Unit 7, Lesson 7, General Pyramids and Cones and their cross-sections. There are two student outcomes as a result of this lesson. One is that students understand the definition of general pyramid and cone, as well as their respective cross-sections. They are similar to the base. 2, students show that if two cones have the same base area and the same height, then cross-sections for the cones that have the same distance from the vertex also have the same area. So part A asks, what similarities do the cross-sections of the pictured figures have? And the similarities that they have, and hopefully that you noticed, is that 1, they are prisms. And 2, that they have the same pentagon base. The difference that the cross-sections have is that in the first one, I'll label it number 1, and I'll label this number 2. The pentagon bases, as you can see, are parallel to each other. And the same goes for the cross-sections. So for number 1, the cross-sections are parallel to the base, whereas that is not the case for number 2. Another thing I'd like to talk about are some properties of these figures. So we already discussed the bases. We have something called faces, and as you can see, we've got rectangular faces here. We also have something called an edge. Okay, so those are where the two faces intersect. It's a line. Okay, and over in this picture we have something called the vertex because it comes to a point. Okay, and there's the face, which is triangular. And of course the base is the pentagon. And then all of these lines here are edges. Please click this link down here and take a look at this video in order to see a demonstration. Come back to this later. Or perhaps you want to finish watching the rest of the video, get all the notes, and then go back and restart it and check out this video. So, of some vocabulary that we've encountered, and please, I'm going to remind you each and every time, transfer this information to your composition notebooks. We're down to the last wire with Regents Prep, and this will be very beneficial. So we have a general cone, and that's a solid figure with a curved or semi-curved base. A general cone has a vertex, just like a pyramid. And then we have a pyramid, which is a general cone with a polygonal base. As we saw in Lesson 6, we can further define pyramids and cones. A general cone with a disk as its base is a circular cone. And a general cone whose vertex lies on the perpendicular line to the base and that passes through the center of the base is right or a right general cone, depending on the shape of the base. The cross-section of a figure is a slice that is taken parallel to the base of the solid. In a general cone, the cross-section will always be a figure that is similar to the base of the cone. The vertex of the cone is the center of dilation. So we definitely want to know the property that we have similar figures. When we have cross-sections, we have parallelism. It's parallel to the base. And of course, the vertex of the cone is the center of dilation. Transfer this to your composition notebooks. Example 1. In the triangular pyramid, a plane passes through the pyramid so that it is parallel to the base and results in the cross-section of triangle A', B', and C'. If the area of triangle ABC is 25 square millimeters, what is the area of triangle A', B', and C'? So here you're going to have to connect what you know about similarity. The first thing what I recognize is that we have two triangles where the prime 1 is similar to the base. I have these two values. The smaller triangle is 3 and the larger triangle is 5. So we have a scale factor of 3 to 5. And they're also similar by the side-side-side similarity criterion. As a result, we can apply the scaling principle for areas of a triangle, that is. Okay, so scaling principle says we can take the scale factor and square it and multiply it to 25 and set that equal to, or get that equal to, a value. So we have 9 over 25ths times 25. These two cancel out and we get 9 left. Now you're probably wondering where I got the 25 from because it's been a little while since you've seen this. This is the area for the larger triangle. And the area of A prime, triangle A prime, B prime, C prime is 9 square millimeters. Please keep in mind that a cross-section is parallel to the base. Therefore, by the triangle side splitter theorem, we can conclude that A prime, B prime splits triangle ABV proportionally. And then a dilation maps A to A prime and B to B prime by the same scale factor. So that's why we're able to use the scale factor in terms of finding the area of the other triangle. Example 2. In the following triangular pyramid, a plane passes through the pyramid so that it is parallel to the base and results in the cross-section of a triangle A prime, B prime, C prime. The altitude from V is drawn. The intersection of the altitude with the base is x, and the intersection of the altitude with the cross-section is x prime. If the distance from x to v is 18 millimeters, the distance from x prime to v is 12 millimeters. And the area of triangle A prime, B prime, C prime is 28 square millimeters. What is the area of triangle ABC? Okay, so let's first dictate what the scale factor is. Because these two triangles are similar, and you could prove them to be similar by angle. We represent scale factor by a constant value k, and that's equal to 18 over 12, which reduces to 3/2. Then in order to find the area of triangle ABC, that's equal to the scale factor times the area of the given triangle A prime, B prime, C prime. So area of triangle ABC is equal to 3 halves squared times 28. So 9/4 times 28. 4 goes into 28 7 times, and 9 times 7 is equal to 63. So the area of triangle ABC is equal to 63 square millimeters. Another theorem we need to add to the composition notebook, and that's the general cone cross-section theorem. If two general cones have the same base area and the same height, then cross-sections for the general cones that have the same distance from the vertex also have the same area. So example 3. The diagram below shows a circular cone and a general pyramid. The bases of the cones are equal in area, and the solids have equal heights. Sketch a slice in each cone that is parallel to the base of the cone and 2/3 closer to the vertex than the base plane. Okay, so I see that I have a quadrilateral base here, and I need to get it like 2/3 closer to the vertex. And then here I have a circular base. So the distance from the slice to the vertex is 1/3 plus 2/3. That gives us a total of 1. So the scale factor from the base to the slice is 1/3. Part B. If the area of the base of the circular cone is 616 square units, find the exact area of the slice shown in the pyramid. So as a result of the areas of the planar regions are related by the square of a scale factor, we know that the area of the base of the circular cone is 616 square units, and we know that they have the same height. We can go ahead and equate that they have the same base areas, having the same distance away from the vertex. So the area of the slice is equal to 1/3 square times 616, which gives us 616 divided by 9 as the answer for the area of the slice. What an awkward number, but it works. Exercises number 1. The area of the base of a cone is 16 square inches, and the height is 10 inches. Find the area of the cross section that has a distance of 5 inches from the vertex. So the area of the cross section is equal to the scale factor, which is 5/10, and that reduces to 1/2 squared times the area of the base of the cone that's given, which is 16. So we get 1/4 times 16, and we know 4 goes into 16 4 times. So the area of the cross section, or the slice, is 4. And of course that's square inches. Number 2, sketch the figure that is formed if the triangular region is rotated around the provided axis. So we took a look at this already last week, or last Thursday to be exact, and you noticed that when you rotated this axis, you ended up with a cone. So as a result, notice that you have a right triangle. When you rotate it about or an axis of rotation 360 degrees, you end up with a figure that's a cone that has a circular base. Number 3, the following pyramids have equal altitudes and both bases are equal in area and are coplanar. That means they share the same plane. Both pyramids, cross-sections are also coplanar. If BC is equal to 3 radical 2, and B prime C prime is 2 radical 3, and the area of TUVWXYZ is 30 square units, what is the area of the cross-section of A prime, B prime, C prime, as well as D prime? Okay, so the area of TUVWXYZ is equal to 30 square units. We're going to designate the scale factor. Is 2/3 divided by 3 radical 2. Square that, multiply it to the area, and get 4 times 3 is 12, and 9 times 2 is 18 times 30. I know 6 goes into 18 3 times, and 6 goes into 35 times, and we go ahead and multiply that. We get 60 divided by 3, which inevitably gives us 20 square units.